All right, hey everybody. So we're gonna be starting about now. So it's our first meeting of the new year. Basically, we're gonna be going over the past USACO December contest. Um, but first, like some announcements. So we recently sent out a Google form. Hopefully, you guys saw it. We sent out a bit before winter break, and it was regarding the lesson plans for like this year, the second semester for the club. And so based off those responses, we've like kind of created a tentative schedule. Basically, the three topics, they're actually all tied for like most interested are USACO, algorithms, and machine learning. And so we decided that we'll probably have around like 4 lessons for USACO, 4 to 6 for algorithms, and 4 to 6 for machine learning. Reasons why are mainly because there's not too much we can like teach like for USACO without going like crazy in depth and like just like fully dedicated to it. So what we're probably gonna do is just mainly go over the contests after like each contest. So like what we're doing today. And then for algorithms, we're gonna be dealing with all sorts of algorithms and probably some that are like applicable or like that can be reused in USACO competitions. And machine learning is just machine learning. So if you guys have any question about this, you guys can always let us know. But that's basically what the structure is going to be roughly looking like as we go into the second semester. And then so last thing is if you guys haven't heard yet, so the first USACO contest was just recently near the end of December. The next one is on January 22nd to 25th. You can find all of like the dates on their website. So you can see the next one is January 22nd and 25th and so on. And just a heads up, the January contest and February contest should roughly like be pretty much same level of difficulty as the December contest. However, the April one, the US Open, should be a bit more difficult if you're like looking to advance. And so I'm gonna stop sharing now, and Josh and Zenkai are gonna continue.
Okay, so we're going to continue with our bronze problems. And well, since we don't know you guys too well, and most of you guys didn't click the USACO role in the Discord server, so just assume that most of you are either at bronze or silver, or you're not doing USACO, which is all right. But yeah, so we're starting with USACO problem 1. And so the problem is called do you know your ABCs? And basically you're given 7 numbers, and the 7 numbers include A, B, C, and then the sum of A and B, the sum of B and C, C and A, and the sum of all 3 numbers, but they are not in order. So your job is basically to find what A, B, and C is. And there's a constraint that A is always A is less than or equal to B and is less than or equal to C. So the while you can try to like brute force it, but it's not really feasible. Plus, there's a much easier way to do it once you like actually make the observation. Basically, A is always the smallest number, and B is always the second smallest number. So you can basically sort this list or this array and then get A and B. So and then find the largest number, which is A plus B plus C, and then subtract A and B from that largest number. And yeah, you basically got the answer. And I believe it's pretty easy to implement. So I'm just gonna show the solution code. Yeah, so basically create an array, you get a scanner, you scan the integers into the array, and then you sort it, and you print it out like that. So yeah, this is this last element, first element, and then second element. So that's basically how it works. Yeah. And here's a C++ solution if you guys programming C++. It's basically pretty similar. Yeah. Yeah, it's basically the same thing. So there's not much to it. So we're gonna continue to the next problem. So okay, this was problem number 3, bronze 3, and so the problem statement says that you've got n cows and it's less than 50, and then they graze on a farm. And then the cows think of the farm as a 2D grid and of cells, made of cells. So it's like a chessboard, and each cell is filled with grass. And so each cow will have an initial coordinate, and they start facing either north or east. And every hour, each cow either stop if there's no grass in her current cell, or they eat the grass in their current cell, and then they move forward in their direction, either north or east, and they never change direction. And if two cows happen to move onto the same cell, they will share the grass. And yeah, so the reason why the problem has the word rut in it is because as they graze, each cow will leave a rut behind her. And yeah, so some cows will eventually stop, but some others will graze infinitely many cells. And your job is to determine the number of cells each cow could eat, or number of cells of grass each cow eats, and print infinite if the cow does not stop. And so the constraints are that you have basically a very large number of, basically the coordinates are very big, and it's not feasible to try to simulate it like by force. So yeah, so you got to figure out a better way to simulate it. And okay, let me show the input format. So the input format is you've got the first number, you've got a number first, and it's the number n, number of cows, and for the next n lines, you will get for each line you'll have a direction, north or east, and two coordinates, and these coordinates are under 10 to the ninth. Yeah, and some sample input. So it looks like that, and then the output, you basically for each cow, you basically print a line stating the number, of cells they could eat. So if during the contest you couldn't figure out the best solution, you should like settle for a just a plain simulation. Just simulate each cow in a 2D Boolean array of cells, I guess. And then when a cow stops, you just mark that cell as false, and so on, and just progress you just progress the time like 1 hour by 1 hour, and try to see which cow stops and which cow has infinite number of grids to eat. I mean cells to eat. But okay. But if you could, then if you could figure it out, then here's the solution. So basically, in algorithm, you'll keep track of the position and direction of each cow, and then you'll try to find the next collision. Well, this is what I call it, but a collision happens when a cow finds an eaten cell, or equivalently hit a rut. So you will do that by checking each cow against another. So basically, you check all possible pairs and see which one will hit a rut first. So basically, you have a cow, and then you check against another cow and see if this cow will hit the rut that the other cow left behind. And so after each collision, you fast forward the time to the next collision, so that you don't waste time simulating each cow moving by one, or eating another cell without hitting red. These are not interesting to us, so we just skip them. Yeah, so we'll have the solution when there are no collisions, basically when no cow so we'll have the solution when there are no collisions left, or that is all cows are either stopped, or they can eat infinite number of grass. I don't have the energy to rewrite this in Java, but they are not too C++ specific, so just bear with me. So start by defining a constant infinity. So yeah, and then we define a class or struct called cow, and then we keep track of what time it has stopped. And if it hasn't stopped yet, then it'll have then we assign infinity to it. So and then we keep track of its position and its direction. Yeah, so it's either so yeah, you probably know what a char is, right? It's a character. Let me turn off the thing again. And this is just the array of cows. We have array of 50 cows. Although n changes, we can just not use the extra cows allocated and just keep it within n. Yeah, so it doesn't really matter. This simplifies the code a bit. And so that's all the variables and definitions. Let's head to the main function. So don't worry about what this means. It just means that, get the number, get the first number and put it into n, basically. And then you have a for loop that looks exactly the same in Java. And you get the direction. So for each line, you get the direction, you get the x, you get the y, and put it into the ith element, the ith cow. And by default, we assign infinity to the time stopped. And if you remember the solution I talked about, we basically just fast forward to the next available, collision event. So yeah, and and if there's no more collisions, we just the function will return infinity and we'll stop, and then we can print the solution. Let's go and see what happens inside the advanced to next event. Okay. So basically, when we check for the next collision, we want to know what is the next, what is the earliest possible collision for each cow, and we'll select the earliest like the earliest collision in all cows that way. So basically, so first, let's see. Okay, so for all cows, we first initialize it to infinity, and if it's not, okay, yeah, when the cows are still moving, that is when it still has a default value of infinity. We'll check for all other cows. We'll compare it to all the other cows and see when it will hit the rut that the other cow left behind, and with the help of the function when hits. Okay, yeah, the when hits function returns a time that the next collision will happen between I and j after the current time, and it will update t sub I when the time is less than when the time so when the time I and j collides, is less than the current value. And yeah, okay. And we also store a min t variable to like so that we know when is the closest collision. And basically that's about it. And so when the min t, when all collisions, when no collisions happen, that is if when hits returns infinity for all possible collisions, that means we have no more collisions left, and we just return infinity to signal that there's, so return infinity to signal that there's no more left. And if there are more collisions left, then we just select the closest collision, and then we advance the and we advance the cow to the it will fast forward the time to the next possible collision, basically. So that's basically how it works. Let's take a look at the when hits function. So yeah, so this function checks if I will hit, or yeah, if I will hit the rut that J left behind, and so it will return infinity if it doesn't happen. So first get the cow from the array, cow I and cow J, and to check if their direction is parallel, then if so, then they will never collide. So we return infinity for that. And so to simplify the function, we just assume for the rest that they're heading. So to simplify the implementation, we just change. We just do a bit of we just modify the cows a little bit so that it's easier for us to. Okay, let me rephrase it. So if the direction of I is east, then we'll change it to north. Not change it to north, but we'll like modify the coordinates so that's a bit easier for us to interpret, to calculate stuff. So just treat it as north, but yeah, but it's we don't lose generality. And so if the rut that J left behind is not in front of I, then we can assume that they will never hit. So we return infinity. And yeah, they're basic. And these two statements are these two clauses are basically calculating when they will hit if. Okay, so these two statements checks if there are any if there's. Okay, these two statements check if there's a possibility of intersection, and there's not, return infinity for that. And yeah, basically that's that. And then if there is a possibility of intersection, then we return basically how much left till I hits J, which is best represented by the y coordinate, the difference in y coordinates. So when basically it'll take y of J minus y of I to get to the current rut that J left behind, and we add that to current time to figure out the next time that will happen. Yeah, and that's basically all there is to it. If this is confusing or if you have any questions, you can ask. Otherwise, we'll move on. We will move on to the next problem, which Josh will explain.
Hi. So this is Bronze question number 2, daisy chains. And the problem statement basically says you have Bessie the cow. She has a certain row, a row of flowers, and there's either anywhere from 1 to 100 flowers in that row of flowers. And then she takes a picture of basically every single combination of flowers in a row together. So first of all, when you're attacking this problem, you gotta think which pictures does she take? And since they're in a row, you have to like basically carve out a chunk of flowers from that row of 100 flowers, or we're assuming 100 for now because that's a worst case scenario. So this is walking away. So assuming we have, let's just start with small because I don't want to draw 100 flowers. We have 5 flowers. Now, how many different pictures would she take of these 5 flowers? So obviously there's the individual pictures. So if she does one picture one at a time, and if she does two flowers at a time, and then 3 flowers at a time, these three, and these three, and then 4 flowers, and then 5 flowers. But there's a simpler way to basically list every single picture she ever takes, and that is to just pick a random flower to be your starting point and a random flower to be your ending point, and just take a picture of all the flowers in between the start and the end point. And so now, how many pictures would she take in total? Well, what happens here is that basically if you want to list every single possible combination, you start iterating through the entire list and getting how do I say this? You go through the entire list and you choose a random flower, and that will be your starting point. Then from that flower onwards, choose another flower, and that will be your end point. And so if you want to write that as code, you can simply make 2 for loops. So you can just do for int I equals 0, I less than, and the array length. So just that for now, and I plus plus. And what that would do, so for right now, we're setting I to be the very first flower. Oh my god, I don't like this. So we're letting I be the very first flower in the picture she takes. So that will be your flower 1, your starting point. And now we want to get a second flower that's after the first flower to be the ending point of the row of pictures she takes. So then we just simply make another for loop and use a different variable. And that will be the second value. So these 2 for loops together, it will grab every single possible like combination of flowers that Bessie will take. So now that you have a for loop set up, you can move on to the next part. So the next part, oh wait, wrong problem. Next part, it says how many of her photos will have a flower that has the average amount of petals on it. And that one, we just simply calculate the amount of petals that are on the flowers in the set of pictures we took. So we have I and we have J, the start and the end. So now just iterate from I to J and get every single, count every single petal on those flowers within that range. And after you get that, you will have the total sum of all the petals within that range of flowers that she took the picture from. And then you have to find you have to see whether there is a flower with the average number of petals that exists within that range. And now there's 2 ways to figure out whether it is the average or not. So you can either, so let's say there are 4 flowers and they add up, there's a total of 20 petals. Right, so with this, you clearly see that the average number of petals per flower is 5 petals. So if there's a flower with 5 petals, then there will be a flower with the average number of petals on it. But now there's 2 ways to do it, to check. You can either take the total amount of flowers, total amount of petals, and divide it by the number of flowers and check it against each flower. Or you could take each flower and multiply it with the total number of flowers and check it against the petal. So you can either take 20 divided by 4 and check whether that equals 5 or not. Or you could take 5 multiplied by the number of flowers, which is 4, and check it against 20. Now, division, what's going to happen with division is division will require a little more work and it will be a little more uncertain. There are ways to make it completely fail-proof, but for now, if you think about it, if it's 21 and you use integers, it'll round or it'll truncate and it'll give you the wrong value. And if you use double, now we're comparing an integer against a double, and that's going to require more code. So a simpler way and straightforward way is just to simply multiply two integers and check it against the bigger value. Since this way, there's no way you get a double, a decimal value. There's nothing like no hassle about this. So it's easier, I guess. And if you do find it, then you just increment the number of pictures that contains an average flower by 1, and you just go through the entire list, and then you just count how many there are. So we have the solution code down here. So you can see these are just setting up the variables, and to shorten this part, what it does is it just creates an array called petals, and each element in the petal array will represent one flower, and it will contain how many petals are on that flower. So integer photos will be counting how many photos contain the average flower. And we iterate through the entire array twice to grab the start index and the end index of the two flowers of the range we're going to take. So every single possible set of flowers is going to be covered by these two for statements. Integer total petals equals 0, so we're initializing the variable. And then we count through how many petals are in that set of array. So I start, j is end, and in that range, count the total number of petals on the flowers. So, and then you add that to total petals. So now total petals has the total amount of petals in that range of flowers. And now what you do here now is you can't just increment the photos by 1 for each average flower you count, because it's not asking how many average flowers she has pictures of, but rather how many photos contain average flowers. So even if a photo has multiple average flowers in it, it only increments the count by 1. So instead of incrementing every time you see an average flower, you set a Boolean variable to true, and then increase it if the Boolean is true at the end after you went through every single picture in that one photo. That way you ensure that each photo will only increase the count by 1 and not by like 2 or 3 if there are more than one average flower. So you count the number of petals in the photo, you check whether each flower in the photo has the average number of flowers, and if there is, you set a variable to true so that later you can increase the total amount of photos by 1. And then at the end, you just print the total amount of photos and you close it, and it's good practice to close it. That way you don't leave any hanging things. So yeah, so that's how this problem will go. It's a bashing problem. And if you, just going on a tangent here, but if you recall complexity time, so we can quickly go over what a complexity time for this problem will look like. Since we're selecting 2 random numbers from this index, so 2 random flowers, it will be n squared, since there are n squared possibilities. Or in actual fact, it's n squared over 2 is the total number combination, but we don't care about divided by 2, we just care about n squared. And then we're iterating through the entire your array again to count the total number of petals. So then you multiply by n. So the time complexity for this program is n cubed. Not very important, but time complexity. This is a bashing problem basically. So capiche? Everyone got that? No questions? Cool. So the next question, this is silver. So silver, it bashing your treatment out the window, since if you look at the previous problem, this is clearly bashable. You have 100 and 1,000. Even when we multiply that together, it's only 100,000. Yeah, but here we have 10 to the 5th power of farms. So it's it's not much bigger, but if you think about it, there are 10 to the 5th power and an unknown amount of cows. So if you multiply it together, it's kind of hard to bash. And so I haven't explained the problem statement. This is silver problem number 1, Cowntagion. So the problem here is that this farmer John, he has a certain amount of farms, and there are rows connecting each farm. And then one of the cow in farm number 1, so that's the very first farm, has a disease, and every step will either cause the number of cows to double or to have one cow from the infected farm move to the next farm. So before you tackle this problem, you first have to come up with a strategy for the problem. So how do we figure out what is the optimal way to spread these cows out so that they reach every single farm? So the end goal is to have at least one infected cow in every single farm. So what is the most optimal way? We try to draw like a sample diagram to represent the scenario. We have farm 1. It's connected to some other farms. And those farms, they can be connected to other farms and so forth. So for now, let's just have our structure be like this. So farm 1 is connected to these 2 farms. This farm is connected to these 2, and this one's connected to that, and that one's connected to this. And if you read the problem statement, you can see that, where is it? There are n-1 roads for n number of farms. What that means is if there are 7 farms, there has to be 6 roads. And if you use some logic, you'll figure out that it is impossible for one farm to sort of like, it's impossible for a closed loop like this to form because that would require an extra piece of road. So the fact that they limit to n-1 roads prevents any of these kind of closed loops thing from happening. So that makes the problem a bit easier. And now the optimal way, if you were thinking about this while I was talking, the optimal way to spread these cows out is to first double the amount of cows here until there are enough cows to spread to every single other farm and still have one remaining here. So for example, at the very start, the optimal way will be to double the amount of cows, so now there's 2 cows, then double it again to get 4 cows. Then spend 1 move each to move 1 cow from farm 1 to an adjacent farm, and the second cow to another adjacent farm. And now there are 1 cow in each farm. Then you repeat the same process. You keep doubling until you have enough cows for every farm and then move them out. That is the optimal solution. And it will make coding a lot easier and also prevents the need for bashing and other things like that. So thinking about this now, how do you know how many cows you want to double up to? At what point do you stop doubling in a farm? Well, if you look at the number of roads, the roads would dictate how many cows you want to send out. So if there are 2 roads, then there's 2 farms you need to send 2 cows to. And which means you need a total, if there are 2 roads, you need 3 cows. One for the farm you're in, 2 for the connected farms. So, and now how do you tell how many times you need to double your cows? Well, if you learn logarithm is, I assume you guys know what logarithm is. Does anybody not know what logarithm is? No? Okay, good. So logarithm, I'm just gonna go over it real quick. So the number of cows you need, since it doubles every time, it's basically 2 to the x, where x is the number of steps, and equals to the total. So in this case, we need 3 cows, or greater than or equal to 3. So every time it doubles, so it'll be 2 to the power of how many times you double it. So it'll be 2 to the 0 will be 1 cow, 2 to the 1 will be 2, then 4, then 8. So this will ensure that it will double on every step. X is the number of steps it takes. And you can rewrite this as log base 2 of 3 equals x. And oh yeah, also it has to be greater than or equal to. So there's this fancy thing called ceiling. So ceiling, it rounds your number up no matter what. It's kind of like rounding, but no matter what number you're at, always rounds up. So 1 rounds to 1, 1.1 rounds to 2, not 1. So it rounds up every single time. Since we need to have more than 3 cows and not just exactly 3, so we round up. So yeah, that will be your equation. You, for every farm you're at, you find the number of sub farms that it will lead to. Put that in here, log 2 of that, ceiling, and that's the number of steps it'll take during that farm, or to get the number of cows. And then after that, you need to spend 1 step spreading 1 cow to each one. So then you just add the number of, so instead of 3, just put n. N is the number of sub farms. So log base 2 of n, ceiling plus n. That's the total number of steps you're going to spend at each farm to double the cows until you reach your power amount and spread 1 cow to each farm afterwards. So now, after that, you have a plan. You have your pseudocode that you've written up that you're ready to execute. Now to actually parse the data. So it gives you sample input 1, 2, and since right now we know that the number of farms connected to is equal to the number of roads it has, right? So if for every occurrence that the number of farms shows up, you just add 1 to the number of roads it has. So if 1 shows up 3 times, that means that farm number 1 has 3 roads leading out of it. So this is incorrect sketch, obviously, but bear with me. And then if you see here, farm number 2 will have 1 road leading out of it, and that's to farm 1. Farm 3 has 1 road, farm 4 has 1 road. But now you gotta watch out for one thing. Even though, let's say this farm has 3 roads, it only has 2 sub farms in a way. It only spread out to 2 farms since 1 is already infected. So for every farm that is not farm number 1, it's the number of roads minus 1. So there's actually only 2 subfarms, not 3 subfarms. There's 1 subfarm, not 2 subfarms, and so forth. Farm 1 is the only one where the number of roads matches the number of farms it has to spread to. So after that, once you have all the number of subfarms each farm has, now you can start iterating through it. You go through an entire list of all the farms you have, and for the number of subfarms it has, you just apply this formula, log base 2 of n, ceiling plus n, and you add that to the total number of steps it's going to take. So with all that out of the way, now you can finally get to the coding part. So I think this is the solution code. So we have the scanner, we have the input, and here it just checks. So for whatever number it is, we created an array of farm that's the same length as the number of farms that we total have, and each index of the farm will represent how many rows that farm has. So each time the number appears in a list, we add 1 row to the farm it's in. So at the end, we have an entire list of each farm and how many roads each farm has leading out of it. Now for the next part, we start iterating through all of them. And for and here it just ensures that, for this one, each farm is greater than 1. That just ensures that there is a subfarm of it and it's not like the end of the line. So if it's at the end, you don't need to do any calculation. It hit the end, there's no other farm to spread to. It stops right there. And that just checks that there is a way to get out, like to move forward from that farm. And then next step, int step, and this is the equation we have. So in if you learn about logarithm, you know there is a property like this. It's a bit more complex math, but log base a of b is equal to log of b divided by log of a. So that is that's why you guys gotta stay in math. Even if you want to go to comp sci, math is very important. You need to know things like this to be able to solve problems. So with this, log base a of b equals log b over log a, which means log base 2 of n is equal to log of n over log of 2. And that way we can write it in Java. So here we have log of n minus or divided by log of 2. And then we round it. Okay, so Java also has a math.ceiling thing, but I was kind of out of it. So I did integer. So integer, it truncates. So if you have like 3.5, it truncates to 3. And then you just add 1 to it to round up. So yeah. So that's the number of steps it's going to take. And then for each steps, you also add the number of rows leading out. So assuming we get the answer of 3 times it has to double, then you add for every road it has leading out, you add another 1. So that it will be this part for each farm. You just add the number of rows leading out of it. Then you add that total number of steps to total, which isn't really necessary, but it's there. So you contribute to the total amount, and now you can print out total. So that is, that is the solution code. Yeah, did everyone get that? Cool.
So yeah, I think we're done for now. There's some more solutions in the USACO text channel on Discord for bronze number 3, so you guys can check that out if like you're still confused or something. We went a teeny bit over time, but that's okay. Hopefully, guys, you learned something. we'll see you guys back next week, and we'll probably be doing something related to algorithms or machine learning. If you guys have any questions, you guys can let us know now or message us later. Otherwise, I'll end the meeting pretty soon. Okay, I'm ending the meeting. Hop on Discord very quickly.